Welcome to lecture 9. We'll move on to the important topic of valuations and valuation rings. We'll see a somewhat analytic perspective to V rings. Okay, so lecture 9, valuations and valuation rings. Okay, so we'll start with the definition of a totally ordered abelian group. So we'll call gamma with this addition operation and this ordering a totally ordered abelian group if the gamma is an abelian group under the operation plus is greater than equal to is a total order on this abelian group. So what does that mean? If you give me any two elements, say gamma 1 and gamma 2 of this group gamma, then we can compare them. Either gamma 1 is larger than or equal to gamma 2 or gamma 2 is larger than or equal to gamma 1. If both of these equalities hold, then inequalities hold, then that means that gamma 1 equals gamma 2. Okay, so furthermore, we have this notion of antisymmetry. That is, if gamma 1 is larger than or equal to gamma 2 and gamma 2 is larger than or equal to gamma 1, this just means that gamma 1, gamma 2 are the same. And we have this transitive notion that if this third element gamma 3, and suppose it has this, we have this property that gamma 1 is larger than or equal to gamma 2 and that gamma 2 is larger than or equal to gamma 3, then what we have is that gamma 1 is larger than or equal to gamma 3. Okay, these are the properties satisfied by this ordering greater than or equal to, and we have some sort of compatibility between plus and greater than or equal to. So if you give me any other random element, say delta, in the group, and if you have two elements gamma 1 and gamma 2 with the property that gamma 1 is larger than or equal to gamma 2, then you can add delta to both sides and that preserves the inequality. So if gamma 1 is larger than or equal to gamma 2, then gamma 1 plus delta is larger than or equal to gamma 2 plus delta. Okay, and some more pieces of notation which are fairly obvious. So we'll say that gamma 1 is larger than gamma 2 or strictly larger than gamma 2 if gamma 1 is larger than or equal to gamma 2 and in fact gamma 1 is not equal to gamma 2. And similarly, I'll say that gamma 1 is less than or equal to gamma 2 if it just means that gamma 2 is larger than or equal to gamma 1. And similarly, I'll say that gamma 1 is strictly less than gamma 2 if gamma 2 is in fact strictly larger than gamma 1. Okay, and if I have two elements gamma 1 and gamma 2 with the property that gamma 1 is larger than or equal to gamma 2, then I'll call the minimum of gamma 1 and gamma 2, I'll just define it to be gamma 2. Okay, so these were some precursors about totally ordered abelian groups. Some immediate lemmas. If I have a totally ordered abelian group, then that group has to be torsion free. So proof So suppose you take an element gamma, and suppose without loss of generality this element is not the identity element of gamma, and now since gamma is totally ordered, I need to show that gamma is larger than, we know that gamma is larger than 0 or gamma is less than 0, and again without loss of generality let me just assume that gamma is larger than 0. And now you take a natural number larger than or equal to 2. Now if you add gamma n times, that's the same as n times gamma by definition. I'm adding gamma n times, but just write this as adding gamma n minus 1 times to gamma. And now if you use the compatibility relation, this is larger than, each of the gammas are larger than or equal to 0. So if you use the compatibility property, then you get that the sum of n minus 1 times gamma has to be larger than or equal to 0. So this is larger than or equal to gamma, so this must be larger than 0. So this is by assumption that gamma is larger than 0. So if gamma is larger than 0, then gamma plus gamma is larger than 0, gamma plus gamma plus gamma is larger than 0, and so on. And so n times gamma is not 0, and so we've shown that gamma is torsion free. Okay. I want to move on to the definition of valuations. So let K be a field and let gamma with plus and greater than or equal to be a totally ordered abelian group. So we will call a function from k star, so it's all the elements of k that's not 0, so it's k minus 0. So we'll call a function from k star to gamma, so we'll call it a valuation if for all elements alpha and beta in k star, what do we have? Satisfies two properties. So if the two elements are not 0, then the product in this field is also not 0. So I can look at alpha times beta. So the valuation of alpha times beta is the valuation of alpha plus the valuation of beta. That's the first property. And if it happens that alpha plus beta is not 0, then it belongs to k star and I can look at its valuation. This is larger than or equal to the minimum of V alpha comma V beta. Okay. So a function from k star to gamma is called a valuation if it satisfies properties 1 and 2. And the second property is often called the ultrametric property. Okay. Yeah, so this function V is called the valuation. Okay. And associated to this valuation, I'll define the set O. It depends on this function V and this field K. It consists of 0 and all the elements in K star with the property that its valuation is larger than the identity element of gamma. and I'll define another set MV, which consists of all elements in the set OKV with the property that either alpha is 0, or if it belongs to K star, then its valuation is larger, strictly larger than the identity element of gamma. Okay, so what we want to show is that this set OKV is in fact a local ring with maximal ideal MV. Okay, that's why I did not have these notations. So we call OKV a valuation ring. For the valuation V. So right now OKV is just a set. So let's try to show that it's in fact a ring. So some lemmas. The valuation of 1 which is in K is in fact the 0 element of gamma. And so a quick proof. Well, what's the valuation of 1? Well, 1 equals 1 times 1, and the properties of valuation is that when you multiply two elements and take the valuation, it's the sum of the valuations. But the valuation of 1 times 1 is just the valuation of 1. Now that equals 2 times the valuation of 1. But gamma is an abelian group, so if you just subtract the valuation of 1 from both sides, we get that the valuation of 1 is in fact the identity element of gamma. Okay, so this completes the proof of the lemma. Okay, in a similar lemma, the valuation of minus 1 is also in fact 0. And again, why? Let's play a similar trick. What's the valuation of minus 1 times minus 1? Well, minus 1 times minus 1 is just 1. So this in fact equals the valuation of 1, which is in fact 0 by the previous lemma. But if you multiply two elements and take the valuation, that's just the sum of the valuation. So the left hand side is the valuation of minus 1 plus the valuation of minus 1. Now that equals the identity element of gamma. So we get that 2 times the valuation of minus 1 is in fact the identity element of gamma. But we've just shown earlier that gamma is torsion free. This was lemma 21. So this is only possible. So you have an element that when you add it, when you multiply 2, you get 0, the identity element of gamma. So this is only possible if the valuation of minus 1 is in fact 0. Okay, so this proves the lemma. Okay, now let's move on to the proposition. 24, that the set I defined OKV is in fact a subring of K. So by construction, we have that 0 belongs to OKV. And we've just shown that 1 belongs to OKV since its valuation is the identity element of gamma by lemma 22. So what we now have to show is that this set is closed under multiplication and addition. So that's our first claim, is that OKV is closed under multiplication. So why? So suppose you take two elements, alpha and beta, that belong to the set OKV. Now if alpha is 0 or beta is 0, then the product has to be 0 and it belongs to OKV. So without loss of generality, suppose that alpha is not 0 and beta is not 0 and they both belong to OKV. So what does it mean for a non-zero element to belong to OKV? The valuation of alpha is larger than or equal to the identity element of gamma, and the valuation of beta is larger than or equal to the identity element of gamma. Since alpha is not 0 and beta is not 0, we have that alpha beta is not 0. So to prove the claim, we need to show that this product belongs to OKV. What that means is that we need to show that the valuation of alpha beta is larger than or equal to the identity element of gamma. But how do we do it? We use properties of valuations. So specifically the first property, the valuation of alpha beta is the valuation of alpha plus the valuation of beta. But now using the fact that the plus sign and the ordering are compatible, we get that the valuation of alpha is larger than or equal to the identity element of gamma, and the valuation of beta is larger than or equal to the identity element of gamma. So we're using compatibility. But the identity element plus the identity element of gamma just equals the identity element. So thus, valuation of alpha beta is larger than or equal to the identity element of gamma, and this just means that alpha times beta belongs to OKV. So we prove the claim that OKV is closed under multiplication. Okay. So the next claim is that OKV is closed under addition. Again, why? Now suppose you take two elements alpha and beta in OKV. Now if alpha is 0, then what's alpha plus beta? That's just beta, and so that must belong to OKV. And similarly, if beta is 0, then alpha plus beta is just alpha, and that belongs to OKV. And if alpha plus beta is 0, that also belongs to OKV. It's by construction. And so we just suppose without loss of generality that alpha is not 0, beta is not 0, and alpha plus beta is not 0. And once again, since alpha and beta belong to OKV, we have that the valuation of alpha is larger than or equal to the identity element of gamma, and the valuation of beta is larger than or equal to the identity element of gamma. And what we want to show, that alpha plus beta belongs to OKV, alpha plus beta, by assumption is not 0, so what we want to show is that alpha plus beta, its valuation is larger than or equal to the identity element of gamma. Okay, and now if you use property 2, this is what we call the ultrametric property. We have that valuation of alpha plus beta is larger than or equal to the minimum of the valuation of alpha and the valuation of beta, but both valuation of alpha and valuation of beta, by the fact that alpha and beta belong to OKV, they're both larger than or equal to the identity element of gamma. So the minimum should also be larger than or equal to the identity element of gamma, because both of them are larger than or equal to the identity element of gamma. Okay, and so this just means that alpha plus beta belongs to OKV. And so thus we've shown that OKV is closed under addition. So we've shown that OKV contains 0, 1, it's closed under addition and multiplication, and this proves the proposition. So that's why we are calling OKV a ring. Remember, we call this a valuation ring. So the next proposition is OKV in fact turns out to be a V ring from the previous lecture. And again, what does it mean and what do we need to show? So we need to show that if you have an element beta that's not 0 in K, then either that element beta belongs to OKV or its inverse belongs to OKV. This will automatically show that the fraction field of OKV is in fact K. So suppose beta is not in OKV. Now since we have a total order, on gamma, the valuation of beta, well, it must either be larger than 0 or it must be equal to 0 or it must be less than 0. Now in the first two cases, if the valuation of beta is larger than 0, then beta belongs to OKV. If the valuation of beta is equal to 0, by which I mean the identity element of gamma, then also beta belongs to OKV. But we are working with this assumption that beta does not belong to OKV. So the first two cases under this assumption cannot occur. So what remains is that the valuation of beta should be strictly less than 0. So now suppose the valuation of beta, this is the remaining case, that is strictly less than 0. Now I have that the valuation of beta times beta inverse, but what happens when you multiply beta and beta inverse? You get the valuation of 1. So if you multiply beta and beta inverse, you get 1. So the valuation of beta times beta inverse is the valuation of 1. But what's the valuation of 1? That's the identity element of gamma. And what's the valuation of beta times beta inverse? This is the valuation of beta plus the valuation of beta inverse. Okay, so let's box this. Now again, working with the assumption that the valuation of beta is strictly less than the identity element of gamma. And now if you use compatibility, and we add the valuation of beta inverse to both sides, what do we get? We get the valuation of beta plus the valuation of beta inverse is strictly less than the valuation of beta inverse. Okay, but what's the valuation of beta plus valuation of beta inverse? We've just shown that the valuation of beta plus the valuation of beta inverse is 0. So we get that the identity element of gamma. So we get that the identity element of gamma is strictly less than the valuation of beta inverse. That is, the valuation of beta inverse is strictly larger than the identity element of gamma, and so this means that beta inverse should belong to OKB. Okay, so we've shown that this valuation ring OKV is in fact a V ring, because we've shown that if the non-zero element beta doesn't belong to OKV, then its inverse in fact belongs to OKV. So we've actually shown something stronger. So in fact, if beta is not 0 and it doesn't belong to OKV, we've shown that its inverse belongs to MV. Okay, so this completes the proof of the proposition. And an immediate corollary using the properties of V rings from the previous lecture. Let's call it corollary 26. So it follows immediately from all the properties we discussed in the previous lecture. So OKV is a local ring. The fraction field of OKV equals K, and OKV is integrally closed. Okay. So the first property says that it's a local ring. So you can ask, what is the maximal ideal of OKV? So we've suggestively denoted this MV. So it'll turn out that MV is the maximal ideal of OKV. So small proposition before that. Suppose you have an element alpha in this valuation ring OKV. I want to study the maximal ideal, which turns out to studying the units of this ring. So an element is a unit in this valuation ring if and only if its valuation is the identity element of gamma. So suppose you have an element whose valuation is the identity element of gamma. We want to show this implication that alpha is a unit. So how do we show that? Well, alpha times alpha inverse equals 1. And so if you just take valuation on both sides, you get valuation of alpha times alpha inverse is the valuation of 1. But by using properties of valuations, valuation of the product is nothing but the sum of the valuations. And we've also seen that the valuation of 1 is the identity element of gamma. Now we already have that the valuation of alpha by assumption is the identity element of gamma. So we have that the identity element of gamma plus the valuation of alpha inverse equals the identity element of gamma, which means that the valuation of alpha inverse is the identity element of gamma. And so this means that alpha inverse, by definition of the valuation ring, should belong to OKV. So the inverse of alpha, alpha inverse, also belongs to the ring. That's another way of saying that alpha is a unit in OKV, since its inverse also belongs to OKV, and that is alpha belongs to OKV cross. Okay, so we've shown the implication. If V of alpha is the identity element of gamma, then alpha is a unit in the valuation ring. Now conversely, suppose alpha is a unit in the valuation ring, we need to show that its valuation is 0. We want to show that the valuation is the identity element of gamma. So what does it mean for it to be a unit? Its inverse also belongs to OKV, and since both alpha and alpha inverse belong to OKV, what do we have? So we have that the valuation of alpha is larger than or equal to the identity element of gamma, and the valuation of alpha inverse is larger than or equal to the identity element of gamma. Okay. Now we want to show that the valuation of alpha in fact equals the identity element of gamma. So suppose, for the sake of contradiction, that the valuation of alpha is strictly larger than the identity element of gamma. Now again, there are only few tricks to play. What we have is that the valuation of alpha times alpha inverse, well, the alpha times alpha inverse equals 1, and we've seen that its valuation is the identity element of gamma, and we also seen that the valuation of a product is the sum of the valuations. And now again, by using compatibility, what do we have? We have that the valuation of alpha inverse is larger than or equal to the identity element of gamma, and adding the valuation of alpha to both sides, we get valuation of alpha plus the valuation of alpha inverse is larger than or equal to the valuation of alpha, which on the one hand by assumption is strictly larger than the valuation of the identity element, but on the other hand the valuation of alpha plus the valuation of alpha inverse equals the identity element of gamma. Okay, so we get contradiction that the identity element of gamma is strictly larger than the identity element of gamma, but they have to be equal. Thus, the only possibility, if alpha belongs to the units of the valuation ring, is that its valuation must equal the identity element of gamma. Okay, so this proves the proposition. Okay, and so an immediate corollary to this proposition is that the maximal ideal of OKV equals MV. Okay, let's go to the proof of corollary 28. And let's start by recalling what MV was. MV was all the elements of the valuation ring OKV such that either the element alpha is 0 or its valuation is strictly larger than the identity element of gamma. Okay, so the first thing we'll show is that this set is in fact an ideal of OKV. So what do we need to show? So we need to show, first of all, that 0 belongs to MV, but this is true by construction. We need to show that MV is closed under addition, and the argument is similar to showing that OKV is closed under addition. So suppose you have two elements, alpha and beta in MV. Now if alpha is 0, then alpha plus beta is just beta, so it should belong to MV. If beta is 0, then alpha plus beta is alpha, and that belongs to MV. And if alpha plus beta is 0, then alpha plus beta belongs to MV again. So without loss of generality, suppose alpha is not 0, beta is not 0, and that alpha plus beta is not 0. Since alpha is not 0 and alpha belongs to MV, we have that its valuation must be strictly larger than the identity element of gamma, and similarly, since beta is not 0 and it belongs to MV, we have that its valuation is strictly larger than the identity element of gamma. And so the minimum of the valuation of alpha and beta must be one of the valuation of alpha and beta, and just say for simplicity that is the valuation of beta, and what we have is that the minimum is strictly larger than 0. And thus, by the ultrametric property, what do we have? We have that the valuation of alpha plus beta is larger than the minimum, larger than equal to the minimum of the valuation of alpha and the valuation of beta, which is strictly larger than the identity element of gamma. And since the valuation of alpha plus beta is strictly larger than the identity element of gamma, this means that alpha plus beta should belong to MV. And hence, MV is closed under addition. Okay, and now the last property that we need to check to show that MV is an ideal of OKV is that it's closed under scalar multiplication. So suppose you have an element little r in OKV and alpha in MV. Now again, the same argument, if r is 0 or alpha is 0, then r times alpha is just 0, which belongs to MV by construction. So again, without loss of generality, just assume that r is not 0 and that alpha is not 0. And so what does that mean? Since r is in OKV, valuation of r is strictly or larger than equal to the identity element of gamma, since r belongs to OKV. And the valuation of alpha is strictly larger than the identity element of gamma, since alpha belongs to MKB or MV. And so now if you use properties of valuations, if you multiply out R times alpha and take its valuation, it's the valuation of R plus the valuation of alpha. But the valuation of R is larger than or equal to 0, the identity element of gamma. So by using compatibility, this is larger than or equal to the valuation of alpha. And since alpha is an MV, this is strictly larger than the identity element of gamma. And so thus, since the valuation of R alpha is strictly larger than the identity element of gamma, we have R alpha belongs to MV. And so MV is closer to a scalar multiplication. Okay, so this proves the claim that MV is an ideal. Of OKV. Now what we want to show is that MV is the maximal ideal of OKV. So suppose so we already shown that OKV being a valuation ring is a V ring, so it's a local ring, so it has a unique maximal ideal. So suppose I is the maximal ideal of OKV. We want to show that it's equal to MV. So it's enough to show, since it's maximal, that I lives inside MV. Okay. So take an element alpha in I. Since alpha belongs to OKV, we have that the valuation of alpha is larger than or equal to the identity element of gamma. And now since I is a proper ideal, alpha cannot be a unit. Since otherwise, if alpha belongs to I as a unit, then we would get that the ideal is in fact the whole of the ring. So we have that this element alpha, its valuation is larger than or equal to the identity element of gamma. It's not a unit. So by proposition 27, what do we have? Its valuation cannot be equal to 0, so it must be strictly larger than, cannot be equal to the identity element of gamma, so its valuation has to be strictly larger than the identity element of gamma. This just means that alpha belongs to MV. Okay. So we are making this assumption that this element alpha is not 0. If alpha is 0, then alpha belongs to MV automatically. Okay, so what we've shown is that this maximal ideal sits inside MV, and so this just means that this maximal ideal must equal MV. Okay, so this proves the corollary. And so just to summarize things, if you have a valuation on a field K, then you can decompose the field into its valuation ring and a disjoint copy of all the elements of the field that are not in the valuation ring. Now all the elements in the valuation ring have the property that they're characterized by the property that these are elements of the field, with the property that its valuation is larger than or equal to the identity element of gamma, and everything that's in the field but not in the valuation ring, these are characterized by the property that its elements of the field with valuation strictly less than the identity element of gamma. And now for the valuation ring itself, you have this unique maximal ideal MV, and you have the units. And since OKV is a local ring, you can write this as a disjoint union of its units and its maximal ideal. And again, you can characterize the maximal ideal on the units as follows using the valuation. The elements of the units of OKV cross are elements of OKV with the property that its valuation equals the identity element of gamma, and the elements of the maximal ideal are all the elements of OKV whose valuation are strictly larger than the identity element of gamma. Thank you.